Thank you for a wonderful introduction. I'm very delighted today to discuss with you our latest study where we compared surface plasma resonance imaging and ELISA's performance for the analysis of human growth hormone in spiked human serum. Briefly, I will cover the following topics. I will start off with a general explanation of ELISA and surface plasma resonance imaging technology. In addition, I will spend a little time going over the biological role of human growth hormone and discuss its clinical application. Finally, I will present to you how we set up our study to measure human growth hormone in spiked human serum. An example of commonly used immunoassay is enzyme-linked immunosorbent assay, better known as ELISA. It's a test that uses antibodies and color change to identify a protein of interest. ELISAs are performed in a 96-well plate, which permits high throughput results. Immunocapture antibodies are coated and dried in microplate wells, and samples are then incubated in the wells. The target protein is thus bound in the well by the capture antibody, after which the unbound sample material is washed away. A second detector antibody, as shown here, is then added, which binds to a different epitope on the immobilized target protein. This detector antibody is labeled with biotin, which provides an attachment point for some kind of label. In this particular sandwich assay, they utilize horseradish peroxidase as the label, which is tagged with streptoavidin, which inherently binds to the biotin. A substrate like TMB is then added, where it's converted by horseradish peroxidase into a colorful product which can be read by most standard spectrophotometric plate readers. Now, an alternative to the traditional immunoassay methods is surface plasma resonance-based immunosensors. Before presenting surface plasma resonance, I need to introduce to you the concept of total internal reflection. When a light beam hits a half circular prism, the light is bent towards the plane interface, when it's passing from a denser medium to a less dense one. Here in this example, going from glass to air. Now, changing the angle of incidence changes the outcoming light until a critical angle is reached. At this point, all the incoming light is reflected within the circular prism, and this is called total internal reflection. Surface plasma resonance occurs under total internal reflection conditions. So when you shine a p-polarized light through a prism on a sensor chip with a thin metal film on top, about 50 nanometer thickness, the light can interact with the free electrons of the metal layer, inducing a wave-like oscillation of the free electrons and thereby reducing the reflected light intensity. The angle at which the maximum loss of the reflected light intensity occurs is called the resonance angle, or SPR angle. Now, upon analyte binding, the surface plasma resonance conditions are perturbed, resulting in a shift of the SPR angle, and this change is used to provide information on the kinetics. Here's an example of a kinetic curve. Initial step is to functionalize ligands on the surface of the chip, and then you inject your sample, and as analyte bind to your surface over time, you will observe a change in the reflected light intensity. Now, there is a satisfactory linear relationship between signal change and mass concentration of analyte. The SPR signal, which is expressed in resonance units, is therefore a measure of mass concentration at the sensor chip surface. This means that the analyte and ligand association and dissociation can be observed, and ultimately rate constants as well as equilibrium constants can be calculated. I'd like to point out that biomolecular interactions is not limited to proteins. Interactions between DNA-DNA, DNA-protein, lipid-protein, and hybrid systems of biomolecules and non-biological surfaces can also be investigated with surface plasma resonance. So are on rates and off rates really important to know? Well, in some cases, yes, and I will provide you with an example. During the discovery process, scientists assess the kinetics of the drug of interest with a target protein, and often will only look at measuring the binding affinity at the early process of the development. However, in certain situations, compounds with the same affinity could have different on and off rates, which inherently can have very different biological activity profile. Now, slow off rate means increased resonant time, better duration of action for a drug. Or fast on rates could improve in vivo efficacy, where agonist concentrations are high. Understanding the on and off rates may help us reconcile, for example, mismatches in efficacy, selectivity, or safety between human and animal laboratory species. I would like to highlight that association rates are related to the structure of the compound and to the dosage, while dissociation rates are solely dependent on the molecular structure. Finally, understanding the full kinetic profile can help shape the clinical profile of a drug that are important to patients: efficacy, safety, duration of action, and greater tolerability. The system that I'm using in my laboratory is a surface plasma resonance imaging system from HORIBA Scientific. The imaging component of the system allows you to visualize the whole of the biochip through a video CCD camera. This design enables the biochips to be prepared in an array format, with each active spot providing SPR information simultaneously. The high-resolution CCD video camera provides real-time difference images across the array format, with up to 400 active spots. It captures all of the local changes at the surface of the biochip, providing detailed information on molecular binding, biomolecular interactions, and kinetic processes. Data is recorded as intensity variation of the reflected light at a fixed angle for each region of interest selected. A digital image is produced in real time together with the relative sensorgram. This arrangement provides for superior experimental robustness over systems that use independent channels for parallel measurements. For example, different elements of the array can be reserved for positive and negative controls whose measurements are collected at the same time and under the same condition as experimental samples. Because of all these capabilities, the surface plasma resonance imaging platform is not limited to biomedical research, but also found applications in food science, environmental, and agricultural science. We currently have the OpenPlex system from HORIBA Scientific in our laboratory, and here's an illustration of the SPRi optical system. A polarized light from a laser diode is sent towards the functionalized gold surface through a high refractive index prism in order to illuminate the entire spotted biochip. After reflection on the chip, the beam is intercepted by the CCD camera, where it collects the output signal as variations in reflectivity. And here's an image of the biochip that we use, and this is the holder for the biochip. There are two established techniques for biomarkers detection with surface plasma resonance. One is a label-free method where you directly detect the analyte. However, if your analyte concentration falls below the limit of detection of the instrument, you need to resort to a sandwich type assay in order to amplify the SPRi signal. To your right is an example where they use gold nanoparticles tagged to the detection antibodies, and the amplification occurred as a result of the coupling between the localized surface plasma resonance of the gold nanoparticles and the propagating surface plasma resonance of the gold film. We have chosen human growth hormone as our model biomarker, and also better known as somatotropin. It's a 22,000 Dalton polypeptide comprised of 191 amino acids. Human growth hormone is synthesized by the pituitary gland and directly secreted in the bloodstream. The release of the hormone is mainly controlled by the hypothalamic peptide growth hormone releasing hormone and the somatotropin releasing inhibiting factor. Both factors interact to generate pulsatile waves of growth hormone release, resulting in a widely fluctuating levels in blood with peaks between 50 to 100 nanograms per ml and minimum levels of 0.03 nanograms per ml. For example, if you have an excess level of growth hormone, it can cause the following: gigantism, hyperinsulinemia, impaired glucose tolerance, insulin resistance, and finally diabetes. Now, a lack of human growth hormone produces significantly different problems at various ages. In newborns, for example, in newborn infants, it may cause hypoglycemia, growth failure in later infancy and childhood. And in adults, lean body mass, poor bone density, and a number of psychological symptoms, including poor memory, social withdrawal, and even depression. It's also well known that the recombinant HGH is used excessively in the sporting area, often in combination with anabolic steroids as performance-enhancing agent. Although some of its supposed effects remain the subject of scientific controversy, the recombinant HGH has been widely promoted in the athletic community as an ergogenic aid that can increase muscle hypertrophy and strength and reduce body fat, conferring a competitive advantage to athletes. Two approaches have been developed to detect GH misuse. The first is based on the measurement of pituitary GH isoforms and the ratio of the 22 kilodalton isoform to total GH. The second approach is based on the measurement of insulin-like growth factor 1 and N-terminal propeptide of type 3 procollagen, which increase in a dose-dependent manner in response to growth hormone administration. Both methodologies have been approved by the World Anti-Doping Agency and have led the detection of a number of athletes misusing growth hormone. Doping analysis relies on the determination of prohibited substances that should not be present in the body of an athlete or that should be below a threshold value. In the case of xenobiotics, their mere presence is sufficient to establish a doping offense. However, in the case of human biotics, the analytical method faces the difficulty of distinguishing between endogenous and exogenous origin. Recently, the Lushuka group introduced a new SPRi immunoassay for the simultaneous determination of the 22K and the 20K HGH isoforms directly in human serum samples. The selective determination of the 22K and 20K HGH isoforms in human serum samples in a single assay was possible by using two specific HGH monoclonal antibodies. The detection limit for both hormone isoforms was reported to be 0.9 nanograms per ml. Considering that both the deficiency or excess of HGH have great effect on normal physiology, sensitive and selective methods for the determination of this hormone in a wide range of concentrations in biological samples are needed. To this end, we decided to focus our initial study on enhancing the limit of detection to what has been reported with SPRi. Our goal was to achieve a lower range of 0.03 nanograms per ml. Moreover, since the clinical need requires the monitoring of multiple isoforms of HGH, we considered the Surface Plasmon resonance imaging platform as a perfect match, as it offers the ability to monitor multiple interactions simultaneously, better known as multiplexing. In today's presentation, we will go over the diagnostic potential of direct and amplified-SPRi assays, particularly for the detection of human growth hormone in spiked human serum, and compare it directly to ELISA. First, I will start off with our ELISA study. The experiment was performed using a commercial ELISA kit in which human growth hormone capture antibodies were pre-functionalized to each well. Human growth hormone spiked in human serum was incubated into the wells at 4 degrees Celsius overnight. We chose an overnight incubation as it is recommended by the kit, especially if your goal is to try to detect ultra-low concentration of analyte. After the overnight incubation, the detection antibody with HRP was added into each well for 30 minutes, followed by the chromogen addition, and this was also incubated for 30 minutes. The reaction was then stopped with the stop solution, and the absorption is read at 450 nanometer. Titration curve of HGH spiked in 10% human serum is plotted against the obtained optical density at 450 nanometer. We observed a good linear response, and the limit of detection was determined to be 1 nanograms per ml. The coefficient of variation was 6.5%, suggesting good reproducibility. Now I will describe the difference between direct and amplified-SPRi detection. In direct detection mode, the protein of interest is diluted in serum and then injected, and the resultant SPRi signal represents the binding of protein of interest to capture antibodies. However, if the analyte concentration falls below the limit of detection of the instrument, one can inject sequentially nanoenhancers to amplify or to highlight the analyte of interest. The term nanoenhancer is coined by me, which means quantum dots coated with detection molecule. And in this particular study, the quantum dots were coated with detection antibodies specific to human growth hormone. I decided to use quantum dots to enhance the signal because the majority of the amplified SPR studies were using gold nanoparticle. Now, I have been working with quantum dots for a long time, and early on in my research career, I realized they like to communicate with their neighbors. Now, let me take a moment to explain to you what are quantum dots. Quantum dots are a special class of semiconductors which range from 2 to 10 nanometer in diameter. Because of their unusually high surface to volume ratio, quantum dots display unique optical and electrical properties that are different in character to those of the corresponding bulk material. The most apparent of these is the emission of photons under excitation, which are visible to the human eye as light. Moreover, the wavelength of these photon emission depends not on the material from which the quantum dot is made, but its size. Now, if you'd like to know more about how the quantum dots amplify the SPRi signal, I encourage you to read our latest publication in Scientific Report, where we were able to achieve septomole sensitivity in detecting C-reactive protein in human serum. I will now describe to you a general workflow for our experiments. First, we UV ozone our clean biochip and then perform microwave-assisted chemical linker immobilization, and then deposit the antibodies on the surface of the chip using SPRi Rayer. And then we block our surface with a blocking agent inside the OpenPlex instrument from HORIBA Scientific, and then we measure the interactions at real time. Over the last decade, microwave irradiation has become an alternative to conventional methods in organic synthesis and coating of nanomaterials, offering enhanced speed, reproducibility, and scalability. Microwave irradiation utilizes the ability of electric charges present in liquid or a conducting ion in a solid to transform electromagnetic energy into heat, resulting in reaction rate acceleration. I would like to point out that microwave photon is not sufficiently energetic to break or form bonds, but has an effect on rotation. We went ahead and compared conventional methods of chemical linker modification with microwave-assisted surface functionalization of cysteamine and glutaraldehyde and to assess their influence on the binding interaction between the capture and target molecules. In our lab, we have the CEM Discover LabMate as shown here. We deposited on the Biochip C-reactive protein specific aptamers and a control aptamer that does not bind to C-reactive protein. These results are from our previous work, and the reason I included them is to show you the effectiveness of the microwave-assisted immobilization. After the injection of C-reactive protein under buffered conditions, the change in reflectivity was about 1.3. However, performing the same test on the microwave-treated chip, we saw a greater amount of CRP binding to the chip. Not only did the microwave decrease the procedure time from 4 hours to 15 minutes, but also increased the performance of the sensor, and it was very easy to reproduce. Now I'll describe to you how we prepare the SPRi biosensor surface to detect HGH in serum. We immobilize first 11-mercaptohexadecanoic acid using microwave-assisted technology for 5 minutes at 50 degrees Celsius and 50 watts, followed by the addition of EDC NHS under the same conditions. The surface was then blocked with PEG, also using microwave heating. Finally, the antibodies are spotted on the chip using the SPRi arrayer. I would like to note that all the SPRi results presented next in our presentation will have human growth hormone specific antibodies and IgG antibodies serving as the control. The chip is then placed in the instrument and is blocked at a flow rate 20 microliters per minute with BSA in PBS as the running buffer. Here is the kinetic sensorgram representing the results for the real-time direct detection of human growth hormone in spiked human serum. After establishing a baseline and running buffer, the dilute solution of human growth hormone, 30 nanograms per ml, in spiked 10% human serum was injected into the flow cell, followed by washing with a high ionic strength buffer to remove loosely associating or non-specific biomolecules. The resultant signal was observed to be 9.28% change in reflectivity for HGH antibody surfaces coated, whereas the control sample, the antibody IgG, resulted in 3.9% change in reflectivity. The corresponding concentration gradient is plotted, where each point represents the average value of the reflectivity difference calculated from 3 SPRi kinetic curves for each concentration. The limit of detection was determined to be 3.61 nanograms per ml, and the coefficient of variation of the assay was 4.1%, suggesting very good reproducibility. The introduction of the nanoenhancer after the direct detection of human growth hormone, the concentration here was 30 nanograms per ml in spiked human serum, resulted in an increase of signal to 7.8%, while the control sample had minimal change at 0.78%. In addition, a difference image was recorded to correlate the binding kinetics after injection of the nanoenhancers. The spots that have been pre-functionalized with human growth hormone specific antibodies are intensely illuminated as opposed to the control IgG antibody spots. The correlation between the binding kinetics and the difference image helps further validate the binding interaction between the antibody HGH complex and nanoenhancers. To further investigate the reliability of the biosensor in distinguishing different amounts of HGH present in spiked human serum, we assessed the sensor performance with a range of HGH concentrations. A decrease in SPRi signal was observed as the amount of HGH spiked in human serum was lowered. The corresponding concentration gradient is plotted, where each point represents the average value of the reflectivity difference between the initial and final buffer injections calculated from 3 SPRi kinetic curves for each concentration. The limit of detection was determined to be 9.20 picograms per ml, and the coefficient of variation is 20%. Here we compared SPRi response between direct and amplified detection. Each bar represents the average value of the reflectivity difference, again, between the initial and buffer injections. For the direct detection technique, between 25 and 0.25 picogram, the signal started to plateau, and this is not surprising as these concentrations fall below, extremely below the limit of detection of 3 nanograms per ml. Similarly, for the amplified technique, concentrations below the LOD signal started to plateau, and very little variations in signal was observed. We also decided to assess the specificity of the nano-SPRi biosensor. We chose to inject insulin growth factor 1 spiked in human serum as a control, since growth hormones stimulate the secretion of insulin growth factor 1 through the GH receptor on the hepatocyte membrane. After the injection of the IGF-1 in serum, we sequentially injected the nanoenhancers, and the SPRi signal response was similar to the control surface immobilized with IgG. However, when we injected HGH spiked in serum to the very same spot functionalized with HGH capture antibody, we observe a signal enhancement. Therefore, we can conclude that the nano-SPRi, or the amplified detection method, is very specific. In addition, we performed a correlation analysis using the Pearson correlation coefficient to determine the correlation between the SPRi signal intensity and the ELISA optical density values. A p-value less than 0.01 was considered significant. As illustrated in this graph, there's a very good correlation between the human growth hormone levels in spiked human serum measured by SPRi and ELISA. The R value was 0.9263 for 9 different samples. With ELISA, we were able to determine the equilibrium dissociation constant using GraphPad software. The calculated KD value was approximately 79 nanomolar. The on and off rate could not be determined by ELISA. However, using the ScrubAgen software, the equilibrium dissociation constant was determined using the molecular mass of 22 kilodaltons that corresponds to 1 human growth hormone molecule. The resultant KD was 23 picomolar for direct detection, and the on rate 6.1 times 10 to the power of 7, and the off rate is 1.33 times 10 to the minus 3. This means that 0.13% of the human growth hormone and antibody complexes decay per second. We have learned from this study the sensitivity of ELISA is comparable to SPRi, but nano-SPRi provides you with several order of magnitude improvement in sensitivity, therefore allowing us to measure comfortably the lower biological levels of human growth hormone at 0.03 nanograms per ml. One of the biggest advantages of direct SPRi is that it allows you to measure HGH in serum in a label-free manner. SPRi gives you full kinetic profile, but ELISA only provides affinity values. ELISA can be a reliable technique, however, the method itself is time-consuming, which makes it difficult to use in situations requiring real-time monitoring and multiplexing. I would like to take a moment again and review the difference between SPRi, nano-SPRi, and ELISA. With SPRi, you immobilize a capture antibody on the surface and then inject your sample and measure binding of analyte directly. With nano-SPRi, again, you start off with the capture antibody on the surface and then inject your sample. Analyte will bind, followed by consecutive injection with quantum dots coated with detection antibody. This results in amplification of the SPRi signal. As for ELISA, the multi-well plates arrive from the manufacturer already pre-functionalized with the capture antibody, and then you add your sample. The analyte of interest will bind, and then you add the detection antibody followed by streptoavidin horseradish peroxidase. Now this step in some kits can be combined into one step and then followed by the substrate addition. Finally, I would like to acknowledge two of my former graduate students who performed the experiments that I present to you today. Afat Zaidan conducted the ELISA analysis and Stephen Vance performed the SPRi study. The work was done at JSNN in North Carolina, and as you can see, it's always sunny, and this is why most of us in the photo are squinting. Last and of course not least, I would like to thank all of you who attended this webinar today, and I hope you found it useful. Thank you.